Okay, are there any questions about anything that we are doing or any questions about anything we've covered in the class so far? All right, I'm seeing no's, 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 no's. Good. Well, we're working on sensation and perception. We will finish that today, but we won't get to thinking and intelligence, which is due this weekend. Essay about Michael Kevin Kearney to read, and then post some information. And I also posted an information about police officers in Pittsburgh, Pennsylvania. I like to pick on Pittsburgh because my sisters lived in Pittsburgh, and my little sister's children were taken away from her by the Pittsburgh Police Department because one of her teachers thought that one of her children looked like one of the children on a milk carton, and rather than do their actual work, detective work, where every single one of her children had been born in a hospital in Pittsburgh by her, they took her children away from her, and they owed her $20,000 when it was all over. But the stupidity of the Pittsburgh Police Department, I like to pick on them. So I guess it's okay that it's due this weekend, even though we haven't covered the material for it. The material that I want you to talk about is covered in those two pieces that are available to you to read. So we'll just keep it for the 17th then, this weekend, and fly through that on Tuesday and get into the emotion and motivation for the next weekend. Any other questions? I don't see anybody saying yes, so I am going to move on to the sensation and perception. We stopped right here talking about Gestalt Psychology, which the Gestalt psychologists are German philosophers, psychologists, and they've done a lot of work in psychology on their own. They have a different viewpoint, which is also a part of the idea that I have for you guys to do your essays on at the end of the semester, which is cultural differences. Well, this is a very cultural difference. They look at psychology much differently than we do in the United States. And of course, psychologists in Asian countries look at it differently, and they have different views of the world, just like we have different views of the world. And really what needs to be done is to take into consideration all cultures. That's a variable. Culture is a variable in the way that it determines how we will live our lives. So we're going to go through these terms. Similarity is that we see things based on how we see the world. We see that these 20 dots are not 20 dots. We see them as rows of dots because the similar reds and the similar blacks are placed together by our brain, and so we see them as rows, and all we have to do is change the rows into columns, and we see it as columns, not as 20 dots, which is what it is. It's 20 dots on a page, but it's colored in different ways to make us view it differently. That's similarity. Things that have a similar substance, similar look, we in our brain connect them together. Proximity is the same way. This is not 6 lines. We don't see it as 6 lines. That's what it is. It's 6 lines. But because they are collected together and they are in proximity to each other, we see 3 pairs of lines rather than 6 lines. So proximity, we are prepared to see things that are close together as supposedly being connected together. And then continuity is a little harder to tell, but when this X sort of has a flow to it, and because of that flow, we tend to think of it as continuing on into space. It doesn't just stop right there. It isn't an X and then you're done. This flows off into space, and we can sort of imagine the continuity of this X because of the way that it's drawn. Common fate is a really interesting one because things that move together or have a common fate together are seen as belonging together. And so in this particular video, this GIF that I have here, the middle section is moving together and the round section is moving together. And because when they start moving, we see them as belonging together, and they create a circle and a center that are separate from each other from the major portion of the page too. But as soon as they stop, that information is gone. We cannot see them anymore. We can't tell that there are three different sections here, the main page, the circle that goes this way, and the circle, the middle section that goes that way. We don't see that anymore. When they are moving together, when they have a common fate, we see them as being together. And then the pragnans is a very interesting idea that we don't like things that are esoteric. We like pleasing things. We like things that make sense to us. And there's a statement in English that says a bird in the hand is worth more than two in the bush. Have you ever heard that? Saying a bird in the hand is worth more than two in the bush. So some of you have, some of you haven't. If you're out hunting birds and you need them to be alive, but you don't have a cage with you right now, you're going back, you have a bird in your hand that's alive and you're going to go back and put it in a cage. But, oh, there's two of them in a bush. Right? Well, that's two. That's so much better than one. So I'm going to let go of this one and I'm going to go for two. But there's no guarantee you're going to get either one of those two that are in the bush. The bird in the hand is worth more than the two that are in the bush. What you have is better than what you, it's sort of like, you know, the other side of the fence. It's another saying that, you know, the other side of the fence always looks greener. Not necessarily, right? And when you get on the other side of the fence, guess what the side is that you just came from? The other side of the fence. So it doesn't matter which side you're on, there's always another side of the fence. So a bird in the hand is worth more than two in the bush. And I have this little triangle down there that has a statement in it that many of you have already been looking at as I've been talking, and it does not say a bird in the hand. You may have read it as a bird in the hand, but it does not say a bird in the hand. So how many of you can see that it does not say a bird in the hand? Right. Some of you can see that, and some of you can see it after I've stated it, so now you're looking at it more closely. But it says a bird in the hand. There's two thes, two. But our brain goes, that's stupid, just throws out the other the in most cases. And so our brain is so easily fooled, or fools us so easily, by deciding that this doesn't look right and I'm just not going to pay attention to it. So you have to be very careful of what you're looking at. If it doesn't make sense to your brain's just going to go, nah, I'm not going to handle that. So do you all see that now? So Quinn now sees that, right? So that's called pragnans. We like things that make sense and that are pleasing to our brains, and those things that aren't, our brain just decides, nah, I'm not going to handle that. So also with the eyes, is finishing up on the eye section, there are monocular clues. Mono means one, and ocular for eye. So one eye clues. We can see certain things with one eye closed, or if we even had, lost an eye, we can still see certain things. Depth perception is allowed just one eye. And there's something called interposition, which means by looking at the screen with my picture in it that the window is behind me and I'm in front of the window because I obscure the window. Anything that obscures something else, that thing must be in front of the thing it obscures. So it's called interposition. Close objects obscure far away objects. Relative size is far away objects are smaller than the close objects. And painters do this. They paint everything that's really small must be way in the background. Anything that's bigger must be closer to you in the painting, which makes the painting look more 3D. And linear perspective, if you've ever stood on railroad tracks and looked out over the railroad track in a long distance where it hasn't curved out of view, you see the railroad tracks coming closer and closer and closer and closer together, which is impossible because if they aren't parallel, the train's going to fall off the tracks. So they have to be parallel all the way, but our brain sees it with just one eye. It sees that connection that comes closer and closer together. And then motion parallax, if you're looking out at driving in a car and you look out, don't do this if you're driving. Be a passenger in the car. Looking out at a fence that's going by. Well, this fence has exactly the same fence posts across the pasture, but the fence posts that are closer to the car look like they're going faster past you than the ones in the further back. So nearby objects seem to move faster than the far away objects, and sometimes if they're really close together, they look like they're moving backwards. Wheels, if you're looking at the wheel of a car next to you that's moving really fast, sometimes it looks like it's going backwards. And even the power lines and the telephone lines, if you stare at them long enough while somebody else is driving the car, it looks like they're getting closer and closer and closer to the car that you could just reach out the window and touch them, but no, you can't. They're far away. That's monocular clues. Then binocular clues, there are two that you need both eyes for, and they are retinal disparity and convergence. Retinal disparity is that both eyes receive slightly different information, and combining that information allows the brain to calculate distance. But also, as you look at something that's coming closer and closer and closer to you, it's called convergence. Your eyes are moving closer and closer together, which pulls the muscles of the eye. And you don't pay attention to it. It's something that's in the unconscious, this movement of your muscles. But the constriction of those muscles allows you to determine distance as well. Now, children at a certain age cannot do this until they get to in their teens. They can then do this retinal disparity and convergence. Younger children don't have the ability. They haven't learned how to use this yet. And that's the reason why Cub Scouts do not have a merit badge for distance calculation, but Boy Scouts do have a merit badge, because at Boy Scout level, at the age of a Boy Scout, you should be able to do retinal disparity and convergence, to be able to stand somewhere, look at a tree, and determine how far that tree is from you. That's the end of the sight section. Now let's go on to the hearing section, our ears, right? If a tree falls in the forest, there's a philosophy saying, if a tree falls in the forest and there's nothing there to hear the sound of the tree falling, does it make a sound? That's a philosophical trap, not a psychology question. And what they're trying to get at in that philosophy question is, what is sound? Sound is the vibrations in the atmosphere of the air vibrating because of something making the air vibrate. But is it really a sound if nothing's there to hear it? Well, yeah, the vibrations are still there, whether there's anything there for it to impinge upon or not. So hearing requires a medium of some kind that will vibrate in some way, shape, or form, and the medium can be air or water, liquid or air. Air is not as good as water as a conductor. I had a 10-acre piece of property at one point, and if I was on one end of the 10 acres and my wife was on the other end of the 10 acres, I could yell at her and she could barely hear what I was saying, because air does not propagate the sound waves very well. Water, however, if we had been in a pool that was that long and we got down into the water and I yelled at her, she'd certainly be able to hear it. In fact, a whale on one side of the earth can make a noise and it'll propagate all the way around the earth to the other side of the earth, and a whale on the other side of the earth can actually hear the noise that whale made, which is a problem for all the animals in the ocean because we humans make a huge amount of noise in the ocean, and so they're hearing all that noise and they can't hear each other as well. In fact, sonar that the Navy uses causes major havoc with our mammal friends in the ocean. It's sort of like if a whale was right next to a submarine that was using sonar, it'd be like a person next to you with a gun shooting the gun off right next to your ear. It would blow your eardrums out. And so it's dangerous for them if they're close by at one of our Navy ships that is using sonar. Another thing about this is that in space there's no air and no water. So if as in science fiction shows, they shoot each other and the spaceship blows up and you hear the explosion of the spaceship, you would not hear the explosion of the spaceship on the one that survived. If you're in a spaceship and you're hearing a spaceship explode, it's your spaceship that's exploding because it's propagating through the air in your spaceship. So you better be in your suit in case you want to survive this explosion. So that's an impossible. In fact, the only thing that seems to propagate through space and has now been proven in the last decade is gravity waves. Gravity waves will propagate through space. And that was just proven. Einstein thought so, but there was no way to prove it until about 10 years ago. So sound results from the vibrations in air or water. Sound carries further in water. And timbre is the quality of the sound. If I'm your best friend and I call you up on the phone and you don't see it on your telephone who it is that's calling, and I say, "Hi, how are you?" You know immediately who it is because you recognize my voice, because each person has a different timbre, a different sound in their voice, and that includes the frequency, the amplitude, the cadence of the speaking. So that is a part of hearing. Speech is a timbre of the speech. Frequency and pitch are the way that we can describe the cycles per second of a particular sound wave. So you can see at the bottom here we have, if this is 1 second from, if it's 1 second from this side to this side, and 1 second from this side to this side, then we have a 1 cycle per second and a 5 cycle per second. That's what it would look like on a graph. But we would never be able to hear either of these, no matter how loud they were, because our ears do not pick up sounds lower than 20 hertz. So lower than 20 cycles per second. So the number of cycles completed by a wave in a given amount of time is the frequency, and the cycles per second, or hertz it's called, is the usual method of measuring sound frequency. 1 cycle per second equals 1 hertz. You can call it CPS or you can call it hertz. It's the same thing. But humans only hear from 20 to 20,000 hertz. Remember, this is a spectrum. Some people can hear higher. Some people can hear lower. I used to be able to hear much, much higher. I was in an experiment once, and they turned on the sound equipment for me to be able to hear it in a soundproof room. And as soon as they started to turn the equipment up, I could hear the noise. I was like, I hear it. And they're like, you can't hear it. It's not even registering on our gear. They're like, well, your gear is not precise enough then, because I can hear it. And so I could hear really well. I can't anymore. One of the reasons I can't anymore is because when I was in college at the University of Georgia, there is a bar band. I used to go to a bar called the Warehouse, and there was a band that played there. The band eventually became national, and they are called the B-52s. You may have heard of the B-52s. And REM also started off at the University of Georgia. It was a really great place to live at that time. We had some good bands starting off. But I would stand right at the stage with the speaker right next to my ear, and I can't hear very well out of my right ear anymore because I didn't take care of that. And you've got to take care of your hearing, or later in life you're going to be in trouble. I cannot hear very well out of this ear. Now, when my wife says, "Why aren't you listening to me?" I can use that as an excuse. Well, you're talking in my right ear. I can't hear you out of my right ear. But women tend to speak at a higher pitch. So Mickey Mouse talks at a much higher pitch than most people will talk. And that's a high pitch or high frequency, and I talk at a tendency at a low frequency. Women tend to talk a little bit higher, but less than Mickey Mouse. And there's a spectrum here. Of course, there are some women who speak at lower, and there are some men who speak at higher pitches, but the majority of us fit within that standard distribution curve. 68% of us men speak at a lower frequency, women at a higher frequency, and Mickey Mouse at a very high frequency. Dogs can hear at a much higher frequency than humans can. If you've ever blown on a dog whistle, it's way above 20,000 hertz, and so you don't hear anything. Your ears do not respond to it. Most human ears do not respond to it. But the dog goes crazy because the dog hears it, and the dog's like looking all over for the sound. Where's the sound coming from? Why are you making that sound? So the greater the pitch, the higher the frequency is. And just like bees, bumblebees can see ultraviolet, and we can't see ultraviolet, dogs can hear at a higher frequency than humans can hear. Now there is, some people have taken advantage of this. There is a ringtone for cell phones. The ringtone for the cell phone is way up in the upper teens, like 18, 17,000 hertz. Most parents cannot hear that ringtone. So the children, teenage children who have their cell phones, when they get a phone call, they know they're getting a phone call because they hear the ringtone. Their parents have no idea that they are getting a phone call because they can't hear the sound. Interesting use of that technology. So amplitude is the amount of energy that's in the wave. I'm talking to you at a normal amplitude, but I can talk to you at a much lower amplitude, whisper, or I can yell at you, much higher amplitude. That just scared the cat. So amplitude or intensity of sound can actually damage your eardrums. It's the physical strength of the wave, also described as the loudness, and it is measured in decibels. Anything at 85 decibels or above for a period of time can damage your hearing, and that's me. I was listening to the B-52s at much higher than 85 decibels, and there are some older cell phones that will put out more than 85 decibels. Today, the new cell phones warn you as you increase the volume. It warns you and says, you shouldn't go above this because with your earphones in, you're going to hurt your ears. A lawnmower produces 85 decibels. It's a two-stroke gasoline engine. Some weed whackers are also gasoline-powered two-stroke engines. And that two-stroke engine produces 85 decibels, weed whackers and lawnmowers. But the lawnmower, now, I just told you 85 decibels at unprotected sound, unprotected 85 decibels will damage your ears over a long period of time. But the lawnmower, even though it produces 85 decibels, is less damaging to your ears than the gas-powered weed whacker, which also produces 85 decibels. Why is the gas-powered weed whacker more dangerous than a lawnmower if they both produce 85 decibels? Anybody have any idea? Remember, when you're told a statistic, sometimes you're not told the entire statistic. You've got to look for the rest of the information. How close is a lawnmower to your ear? It's way out there. How close is a weed whacker to your ear? Right here. And it isn't the fact that it produces 85 decibels, it's the fact that 85 decibels gets to your ear and the air dampens down, it doesn't propagate as well, so what's getting to your ears from the lawnmower is not 85 decibels, but what's getting to your ear from the weed whacker is way closer to 85 decibels. If you're using a weed whacker that is not an electric but a gasoline-powered weed whacker, you should have something in your ear like a foam or muffs or something to protect your ears so that you are not getting the 85 decibels in your ear, because it will damage your ear. Eventually, you won't be able to tell the difference in your young age, but in your adult, older age, your hearing will decrease more rapidly because of the damage that was done as a young person. Does that make sense? Okay, I'm seeing yeses. I'm seeing lots of yeses. Okay, good. So this is what an ear sort of looks like. Right? We have the outer ear, which is this part of the ear, and the tunnel that goes up to the tympanic membrane, or we call it the eardrum. The eardrum is not part of the outer ear. The eardrum is part of the middle ear. Even though part of it is right next to the outer ear, the whole eardrum, the entire eardrum, is considered part of the middle ear. The middle ear is for conduction. That's all it does. It's called conductive deafness when it's broken and doesn't work anymore. But what it does is, as I'm talking, that noise is vibrating the air. The air is going in, the air is being vibrated by your speakers on your computers or your phones, and that vibration is ending up going through your outer ear to the eardrum, which then vibrates at exactly the same frequency as I'm talking, and amplitude causes it to go faster, stronger beats, and frequency is the number of beats per second. That tympanic membrane or eardrum, as it is vibrating, it has a bone attached to it, which is attached to another bone, which is attached to another bone, called the hammer, the anvil, and the stirrup. They also vibrate along with the eardrum. The vibrations are then carried, right? They're moved across to the inner ear, which is the part that causes you to hear. You're not really hearing anything yet. You're collecting all that data to send to the organs that will eventually create the electrical signal, which is in the inner ear, not the outer ear or the middle ear. The cochlea, which is shown at the bottom, and the arrows are where you have the electrical signals created that will go to the auditory nerve and end up going to the brain, where you then will take that information and figure out what it is. Right, so that's the cochlea, and this is a closer picture of the cochlea. The cochlea, so far we have air vibrations from the outside going into the middle ear and then going into the cochlea. In the cochlea, it is a liquid. Remember, there's propagation in liquid is much better than propagation through the air. So it ends up in liquid. The propagation of these vibrations end up in the liquid. If the liquid is if there's too much liquid, because you have a cold, for instance, and the liquid is building up and not being released, then the pressure in the cochlea keeps the vibrations from going through very well, and you can't hear very well. Also, if the eardrum has too much pressure from the middle ear, there's too much pressure in there, so it's not able to vibrate as easily, you can't hear as well, and anybody who's been in an airplane recognizes that. So the basilar membrane is the part of the cochlea which has hairs attached to it. And as the waves go through the liquid, the hairs move. And as they move, the base of the hair is attached to the basilar membrane. And that base of the hair, as it goes back and forth, creates an electrical signal that then is sent out through the auditory nerve to the brain. Remember that neurons can only fire at 1,000 times per second. So these are vibrating, and sometimes they're vibrating at 10,000 cycles per second. But the neurons they can't handle 10,000 cycles per second. All they can fire off is at 1,000 cycles per second. So how is it that we hear above 1,000 cycles per second? We'll get to that in just a second. So the auditory nerve is a neural pathway connected to the ear and the brain. And notice also that part of the cochlea also has what's called the semicircular canals that are connected to it. And we'll talk about the semicircular canals as well, because they're a part of the hearing process, and they give us some sensations as well, not hearing, but other types of sensations that's attached to hearing. So the primary auditory cortex is the portion of the temporal lobe that processes sounds. Temporal's on the side, remember, we got the frontal, the parietal, temporal, and occipital lobes. So the two temporal lobes, there are 8 lobes, 4 on either side of the brain. The 2 temporal lobes are the ways that we hear, but mostly the left side is in charge of determining what it is that you're hearing. But the auditory cortex is also part of this, because as I'm talking to you and you understand English, everything that you're hearing is going through your nerve into your auditory association cortex, and you're immediately understanding what it is that I'm saying. But if I also say to you, hablo español, pero un poco solamente y no comprendo, you can't associate any of that with any information. You figure out maybe the guy is talking to me and saying something that I'm supposed to know, but you can't understand it unless you understand Spanish, which I said I speak Spanish a little bit, and I don't comprehend it if somebody's talking to me. So that's the auditory association cortex. So you can hear things, but if your auditory association cortex isn't working, it comes out as, it sounds like gibberish. So do you sound the same on a tape recording? How many of you have heard yourself on a recording of some kind and you sound different? You sound different. I'm seeing lots of me's and yeses. Definitely, we sound different on a recording. How many of you like what you hear on the recording? No, I don't like it. Nope, 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 not me. Yeah, that's right. I don't like it either. I do not like the way I sound on a recording. And I'm sorry to tell you this, but that is the way that everybody else in the universe hears you talking. When you talk to somebody, they hear you the same way you hear yourself on a recording. And I'm sorry to say that, because none of us like the way that we sound on a recording, because we're so used to the way that we sound to ourselves. So why is it that we sound differently on a recording than we do when we're talking? When I'm talking to you, I'm vibrating the air. The air is being picked up by my microphone, being transferred through the sound wave, through the telephone lines or whatever else, however you get the information coming out of your speakers, going into your ear. So you're hearing all the vibrations I'm making from my mouth. I am not hearing only the vibrations that I'm saying, because certainly what I'm saying is going out into my area too and coming right back into my ears so I can hear what I'm saying. But as I'm talking, my head is also vibrating and my vocal cords are vibrating, and the ears are picking up all of those vibrations and combining them together, and that's why we sound differently than we do to ourselves than we do on a recording. Because when the recording is talking to us, all it's picking up and responding back to us is what we said from our mouths. It doesn't include all the rest of this. Does that make sense? I'm seeing yeses. Okay, good. All right. If I ever say anything that doesn't make sense, you put down in the chat box, what? Wait, can you repeat that or say it a different way? So that is, unfortunately, the way we sound to other people is the way we sound on a recording. There are different theories on how we hear. Of course, from 20 hertz to 1,000 hertz is easy because our neurons respond at up to 1,000 hertz. So up to 1,000 hertz, if somebody is talking to us at, or we're listening to something that is 1,000 hertz or below, then the ear are vibrating at 1,000 hertz and the hairs are vibrating at 1,000 hertz and the neurons are firing off at 1,000 hertz. And so it's easy to imagine how our brain is getting that information up to 1,000 hertz. But what happens above 1,000 hertz? And there are two different theories of that. The Volley theory states that one group of these hairs fires off at a lower frequency and other groups fire off at higher frequencies, and depending on which of the different neurons are sending signals to the brain, we will interpret that as being somewhere between 1,000 and 4,000 hertz. But then from 4,000 to 20,000 hertz, there's a whole group of things that happen. The loudness and pitch are related to three things: the type of the hairs that are going off, the location of the hairs that are going off, and the number of the hairs that are being activated in the basilar membrane. That accounts for 4,000 to 20,000. And remember, this is all a spectrum. Some people cannot hear at 20,000 as young kids, but most people, the majority of people, 68% of us, one standard deviation in the normal distribution curve, can hear from 20 hertz to 20,000 hertz. There's a great little thing on Facebook, I think it is, but you can find it on the internet, that makes a noise from 20 to 20,000, and you can listen to it and click on when you can hear the sound and click when the sound disappears again, and that will tell you your range of what you can hear. As I said, my hearing is decreasing rapidly in my old age. Conductive deafness is because the middle ear is the conductor. It conducts from the outer ear, from the world, into the inner ear. It's called conductive deafness if there's any damage to the middle ear, and it can be fixed. We can fix the middle ear. It's very precise surgery, but you can fix the middle ear. Sensory neural deafness comes in two different forms. The cochlea can be broken, so it doesn't work anymore, or the auditory nerve can be broken. The auditory nerve is part of the central nervous system. If it is broken, you cannot fix it. It will not be repairable, at least not now, maybe 50 years from now, because they're getting better and better at being able to produce stem cells that create neurons. Maybe one day they'll be able to actually fix a central nervous system neuron. But if the nerve is damaged, there's nothing we can do at this time. But we can have cochlear implants. And you may have seen people who walk around with little boxes attached to their heads. These are called cochlear implants. They are taking information from the environment electronically and then transferring that electrical energy to the auditory nerve. They can hear because their cochlea has been placed on their head in an electronic form. Has anybody ever seen somebody with a cochlear implant? I've only seen two. In my entire life, I've never seen more than two. None of you? Nobody's saying yes to that one. So I guess, can you all hear me still? Okay, you can still hear me. Got to check. That's why you're supposed to say no or yes for these answers, so I know that you can hear me and that you're still there also. The semicircular canals I pointed out are structures in the inner ear that help monitor the body's movement and position. They do two different things: vestibular sense, which is a sense of body orientation with respect to gravity or equilibrium, and the kinesthetic sense, which is a sense of body position and movement of body parts relative to each other, especially when we're in motion, when we're walking. But this also is partially due to our proprioceptors that are in our muscles all over our body, skeletal muscles. The vestibular sense is kind of interesting. Are any of you certified divers? Going into the ocean, deep into the ocean with scuba? I don't see anybody saying yes. It's like no's, no's. Well, In scuba, every drop of water has weight to it. And you have a buoyancy. You have an ability to float and to go up to the surface. Slowly, but go up to the surface. So there is a point at which your buoyancy is the exact same as the pressure of the water above you. And it's different for each person. But if you hit that sweet spot, your vestibular sense is gone because you have no connection to gravity then. And if you have your eyes closed, you can't tell what's up and what's down. And you just sit there in the water, and the pressure of the water is keeping you down, not pushing you any further down because your buoyancy is keeping you from going any further down, but you're stuck at that stage. Now, if it's really, really dark, you can't tell which way's up and which way's down at that point. However, you can always breathe bubbles, and the bubbles are always going to go up, so you know which way is up at that point. But this is a very interesting aspect to scuba diving. And any of you who have ever been in a pool and you dive under the water, go into a little ball and go round and round in a circle, and then just stop, and with your eyes closed, you lose your sense of gravity for a little bit until you start to float up to the surface again, and then you know that which way is up. But the vestibular sense can be confused by going around in a circle underwater and then just freezing, and your brain is just a little bit confused at that point. And that's the end of hearing. Are there any questions on hearing or sight? I'm seeing nose, nose, nose. The next one is smell, olfaction. And I know that's two different words that mean the same thing. And that's the problem with science. I mean, this is a finger. It's your index finger. It's your pointer finger. It's also a phalange. So there's lots of ways to describe this one finger, one finger. And it's the same way for lots of things in science, and this is just one of them. Smell is called olfaction. So that's the sense of smell. And the little areas in your nose that are right next to your brain are called the olfactory bulbs, and they respond to chemicals, molecules in the air, or water, if you're breathing water in. One type of molecule is a pheromone, and female moth can release a single molecule pheromone, and it will float 1 mile away. And a male moth a mile away can follow that pathway back to the female moth from that pheromone. That's how good their particular olfaction is. Our olfaction is horrible. We don't smell very well. Some of us don't smell good anyway, but we don't smell well. Dogs can smell 10 times better than we can, which is probably why they can smell out the drugs, and they can smell out the explosives, and they can smell out cancer in the body. They can be trained to smell cancer. But these pheromones, a lot of people wondered once if we even had pheromones, and there's some research, some weird research that shows that not only do we have pheromones, but we respond to pheromones. Even though our nose is so bad that we don't know what we're smelling, it is an unconscious smell, we will respond to pheromones. And there's two different ones that I like to use as examples. The first one was they took women to a bar. The women were dressed appropriately. All of them were dressed the same way. So there was no difference in the way that they were dressed. They were all registered as a specific level of beauty. So it wasn't that one was more beautiful than another one was. They were all registered at the same level of beauty. But the difference between them was they were at different levels of their period. So some of them could get pregnant and some of them couldn't get pregnant. And they took them to the bar, and then they marked down every interaction they had with the men in the bar. And it turned out the ones who could get pregnant had way more interactions with men, got more drinks than the other ladies, got more dances than the other ladies. So the men unconsciously were responding to the pheromones that are released by women who are able to get pregnant. This is weird. There was another one. This was the University of Pennsylvania that did this next one. They went out and they found a whole bunch of families that had girls in the families that were somewhere close to puberty, 11 years old, 12 and 13 years of age. And they followed these families for 3 years to see what age the girls went into puberty. And it was really interesting that the girls who had biological men in the family, in other words, men that shared blood with them, their biological, their fathers, their brothers, right, they went into puberty much later than the girls who had stepfathers or stepbrothers who had no biological connection to them. They went into puberty faster, or the female body is responding to the male's pheromones that the male is putting off in some way, shape, or form. That was very, very strange, interesting research on pheromones. This is a picture that I do not want you to memorize. I don't have anywhere in the quizzes or tests that ask you to memorize this particular picture. If you're in biology, in physiology, you might have to memorize these. And of course, if you ever take a class in a master's program, you'll probably have to memorize these as well. But this is the smell bulbs that go up into the brain and produce the nerves that end up going into the brain to tell us that we're smelling something. Have you ever smelled something in a room and went, I don't know what it is, but I'm backing out of this room because I don't want to touch it. I don't have any desire to get near it. Any of you ever had that experience? That smell is horrible. I'm not going in there because I don't want to touch it. Yes, a lot of you have had that experience. I'm sorry to tell you this, but you've already been touched. It touched you. That's why you could smell it, because the chemicals from whatever it was that is making that smell, those chemicals ended up in your nose and in your brain. They got to you, close to your brain. These olfactory bulbs are the closest things to your brain. So you were already touched. A smell, and now we're going into taste. But the reason why they're connected together is because taste is 75% smell. Have any of you ever had a cold and your nose was all stuffed up and things didn't taste right? Any of you? I'm seeing some yeses. Because when your nose isn't working right, you're not going to taste as well. Part of taste is smell. I have a cousin who was a photographer back in the day when photography was all chemical in nature, and these chemicals put off fumes. And so if you're in a dark room, the light's turned off, you've got a red light which doesn't affect the paper, and so you have a fan in that room that pulls air in and pushes air out because these fumes can do damage to you. And her fan died one day, and she was in there all day long, and she blew out all of her olfactory bulbs. She can't smell anymore. She does not smell. Now, I told her that that's a good thing because I think her husband stinks, but I don't mean smell. And she got divorced later, so I guess I was right. But she can't taste. She says she eats food because of its texture, because of the way it feels in the mouth. Mashed potatoes have a specific texture. Steak has a specific texture. Rice pudding has a specific texture. Corn has a specific texture. So she eats because of the texture, not because of the taste. So we know that we have taste buds. Our taste buds are on our tongue, and they respond to very specific chemicals. So we have taste buds that respond to sweet and sour and salty and bitter and umami. And we'll talk about those in just a minute. But in my day, when I was a kid in elementary school, they had this stuff you could put in your mouth, a drink, swish it around in your mouth, and then spit it out. And then they had a black light that would shine on your tongue, and you could see all of your taste buds. All your taste buds would light up. Have any of you ever done that? I know they don't do it now anymore in elementary schools, but some of you may be old enough that you did it in elementary school. All right, nobody has ever done that. All right. I think there is a product you could still get on the internet that does that, but I think that the reason they don't do it anymore in elementary schools is probably because it had some negative consequences, and so they don't do it anymore that way. But I remember my tongue, it was like I looked at my tongue, and my tongue has these little spots on it. And one of my friends' tongue, they're just glowing. Their whole tongue is glowing. And that's because some people have lots of taste buds and some people have less taste buds. It's a spectrum, just like everything else. So these are some of the fastest growing cells in your body. Some of the reasons why some of you may, in your younger years, not like a food, and later in life you like that food, or you don't, or you like a food in younger life and later in life you don't like that food because your taste buds change so rapidly. Also, because they change so rapidly and they grow so fast, a tongue piercing is very different than an ear piercing. How many of you have tongue piercings? Any of you? Nobody's saying yes, so I guess nobody has a tongue piercing. So tongue piercings, when you pierce your, how many of you have ear piercings? Some of you have ear piercings? You have earrings? I got at least one yes out of the group, 2 yeses out of the group. Okay, so earrings, when you have your ear pierced, you have to keep your earring in for a certain amount of time before you can take it out because it'll close back up again. But after it's been in for a little while, it won't close up very fast. And so you can actually leave it out for a little while and then put another one in, and then leave it out for a little while, put another one in. Tongue piercings, when you have your tongue pierced, that piercing has to stay in a lot longer time. In my last class, I had a lady who was 23 years. She's had a piercing, 23 years tongue piercing. Well, her hole is probably now pretty well defined and won't close up very fast. But it'll still close up faster than the ear will. If you take the tongue piercing out and an ear piercing 23 years later, the tongue piercing is going to end up being no longer there much faster than the ear will. Now, my little girl, when we adopted her at 9, she had these little spots in her ear. They weren't pierced anymore, but obviously she had had her ear pierced when she was much younger, both of them. But now they're all closed up. She wants to get them pierced again. Wait until you're 31 when you start dating. So they regenerate very rapidly in the body. Super tasters are the people like my friend who had just a ton of taste buds all over his tongue. It was just covered. I'm a non-taster. Super tasters, there's about 33% of us that are super tasters, 33% of us that are non-tasters, and the rest of us in the middle. So these super tasters taste much more intricately than other people do. A wine taster, remember people who can, people who can, or of people who can spin a glass of wine, sniff it, and taste it, and tell you everything that was used to create that wine. Well, a super taster can easily be trained to do that. A non-taster, I don't care how much training you have, you're never going to be able to do that because you don't taste that intricately. And there's actually a theory that defines weight management and health based on super tasters and non-tasters. Super tasters with a drop of sugar, a drop of a sweetener in tea, oh, that's sweet tea. Non-tasters, They need lots of sugar. When I was a kid, I used to go to a restaurant and I would tell the waitress, bring me a glass of tea with no ice in it. Now, I lived in the north, so they had no idea what sweet tea was. Bring me a glass of tea and then bring me a glass of ice. Separate, 2 glasses, 1 ice, 1 tea. And I would take 12 teaspoons of sugar in the glass of tea, mix it in till it was all in and then pour it over the ice. That's how much sugar I needed before I could taste that it was sweet, which means I'm getting a heck of a lot more carbs and calories than a super taster is. The super taster is most likely thinner than a non-taster because non-tasters are pushing the calories count and the carb count. So super tasters are thinner normally than non-tasters are. But there's another issue with that as well, because super tasters taste so intricately, they hate the taste of broccoli. Non-tasters, not a problem. In fact, lots of vegetables do not taste good to super tasters. They hate the taste of the vegetables. And so they don't get their vegetable minerals and vitamins as much. So I might be, as a non-taster, heavier than a super taster, but I'm getting my minerals and my vitamins from my vegetables because I'll eat any vegetable. I like them more raw than I like them cooked, but I'll eat vegetables. Not a problem. Not to a super taster. They don't taste good. Do you get that? Do you understand the difference there? Again, a spectrum that causes very big differences between people. All right. I know that's a little more biological than the psychological, but you can see how it can affect us. Now, there are 5 different tastes in our tongue. The sweet, we figure that one out. Sour is lemons or sour. Salt, salty. Bitter, quinine. Tonic water has quinine in it, which makes it very bitter. And actually, quinine tonic water with some sugar in it and some lemon in it makes a great lemonade. And it's good for you too, because quinine actually helps with restless leg syndrome, and the people who have a lot of Charlie horses in their legs, quinine helps the Charlie horses. So tonic water is good for that. If any of you are that way, try the tonic water. And then there's umami. Umami responds to monosodium glutamate. Monosodium glutamate is in a lot of different products. Yes, it's in most Asian foods. Chinese food, certainly. Japanese food has monosodium glutamate in it. And I teased you a little bit about that because I said, well, cat doesn't taste very good without it. So, of course, they have to add the monosodium glutamate. But, you know, it's not cat that they're serving you. So, and Chinese foods have lots of monosodium glutamate in it. But go to the store one day and look at foods. Just amazing how much food has monosodium glutamate added to it to make it taste good. Almost every condensed soup that Campbell's makes has monosodium glutamate or high fructose corn syrup in it, either one. And I keep away from both. I don't like either one of them. Remember from our second unit, the biological unit, that people have a lot of glutamine in their system. Glutamine is the excitatory neurotransmitter. Glutamate and glutamine are very similar, and if you eat glutamate, then you will get a higher level of glutamine in your body as it breaks it down, and people react to it badly. And I'm one of those that reacts to it badly. I start sweating, shaking, and if I eat too much of the things that I react to, I start hearing voices, get horrible headaches. It's terrible. So I just stay away from that stuff. It's bad for me, not necessarily bad for you. And then we get to the skin response. Is there any question off of the taste or the smell? Any questions off of those? Nose. I'm seeing nose. I only see 3 no's. Are the rest of you still there? Okay, good. All right. So now we get to the skin responses. The first one I like to talk about is one that most people have never heard of, and that's the galvanic skin response. And that is the resistance in your skin, like electrical resistance. So if your skin is dry, then you have from one point to another point on your palm, so 2 points on your palm. If your skin is dry, the resistance between those is very high. But if you're sweaty, then there's salt, and salt carries electricity, so the resistance decreases, and you can get a more electrical signal through your skin if your skin is a little bit more moist, right? Sweat glands. You can control that. You can actually learn to control the amount of resistance, galvanic skin response in your skin. Why? You can learn to control that. And then some of the other skin responses: touch, pressure, warmth, cold, and pain. We'll talk about each one of those. Well, not warmth and cold, but pressure and pain and touch. And I have a little picture here of a guy warming his hands over a radiator. Some of you may not even recognize what that is. That's hot water radiator. You have hot water going through the radiator, which then radiates the heat into the house. And you don't want to touch them. When they get hot, they get hot. So there is in our skins receptors for touch. And it's not evenly distributed throughout our body. Our lips have way more receptors in them than our fingertips. And the fingertips have way more than our back does. So we can actually draw a picture of a person based on how many receptors there are in the skin. So the lips would be very big because there's more of it there. So this is called a homunculus. And there's one part of it that's blacked out because that's a really big part of skin receptors in that particular area for both male and female. And this is a male because there's other two areas in a female that are very high levels of skin receptors. So this homunculus, you see very large lips, cheeks are pretty large, fingers, palms, and fingertips are very large, but the body itself is kind of small. The forehead is pretty small, and the legs are tiny, but the feet tend to be bigger because they have more receptors in them, and the toes are really tiny because they don't have a lot of receptors in them. But if you smash your toe, you realize that they do have receptors in them. So this picture shows that our lips are probably some of the largest number of receptors in the body, right there in the lips, which is why we don't kiss by touching fingers. We kiss by touching lips because it's more pleasurable to touch your lips together because you have a lot more sensation in your lips. This brings up what's called the 2-point threshold, that if I take 2 pins and put them on your back, not push them into your back because that would hurt, just touch them to your back. If I have them at a specific level apart, you can't tell that there's 2 pins there. I have to move them further apart before you recognize, oh, there's 2 pins touching. Put them here. Nope, can't tell. There's not enough receptors to make the distinguish between the difference. But if you close your eyes and I put those 2 pins on your lips, it'd be very difficult to get them close enough together that you can't tell that there's 2 because there's so many receptors on your lips that you can, 2-point threshold is tiny on your lips, large on your back. And that's called the 2-point threshold, the smallest distance between 2 objects where we can tell they are 2 objects. This is the smallest in the lips and fingertips because of the number of nerves that are packed into those particular areas. Touch is essential, especially in newborns, but touch stimulates brain growth, and there's a research project that showed this. They took baby mice that had just been born to a mother, had a big litter, broke those 2 baby mice litter into 2 different groups, put them into isolates away from their mom. They were not allowed to have their mom near them. So they were given all the food they needed, all the water they needed, all of the air, oxygen they needed. They were kept from the bacteria and viruses. They were given a beautiful environment in which they should flourish. And one group was made different than the other group. And the only difference was they took a paintbrush and they brushed those mice every day, where they didn't brush the other group. So the groups were exactly identical except for the brushing of the mice. When they grew up into adult mice, the adult mice that had been brushed were larger, had more development in their brain, were faster in picking up information, were more intelligent, is basically what we're saying, more intelligent. Their brains were heavier. So touch was really important in the development of those mice, and it's very, very important in the development of the human being as well. Premature babies are placed into an isolate, same thing that we put the little mice into, a area, an environment that is perfect for them to be able to thrive. But they do not thrive unless they're touched, stroked, their hands are massaged, their feet are massaged, their head is stroked, they're talked to. Then they thrive much better than those who have not had that. Touch, proper touch. Touch is important for the growth of the brain. And so pleasant stimulation produces and helps growth. But too much stimulation produces pain. Now, some of you, almost every one of you, should have had a time in your life where something itched. It itches so much. Itch is actually on the verge of pain. It's just below the pain level. It itches. It doesn't hurt. It itches. If you can make it hurt, the itch goes away. If you've ever had like poison ivy, and I know I've asked that question, and some of you have had poison ivy and some of you have not, but poison ivy itches. It's horrible. It's a terrible itch. Just below the pain threshold. So put your hand underneath water, hot and cold water on, so it's warm water, and then slowly turn the cold water off until it gets hotter and hotter and hotter until it's painful to hold your hand where it itches underneath the water. Let it stay there for a little bit. It's painful, but it's not going to burn you yet. Then take your hand out and the itch is gone away. And so is the pain, because the reason for the pain, the hot water, is gone too. You have pushed the itch over the edge, and you at least have some relief from the itch. There's a gait theory of pain, which means that we can only hold so much pain, and it is monitored by our brain. And if we had too much pain, we pass out. We pass out. We can use the gait theory of pain. If your hand hurts and I stomp on your foot, your hand doesn't hurt anymore. Your foot does. So it's a bottleneck. Just like a soda bottle, you drink from the soda bottle, it doesn't go all over you because you can, it concentrates and controls the amount that's going into your mouth. Same thing with the gait theory of pain. We can only have so much pain. But what's interesting, that I was actually, a doctor did this to me once. In my day, you could get a shot in the arm or you got a shot in the butt as a child. And they'd have you pull your pants down and take your arm and get ready for it, this one doctor. And so you didn't know where it was coming. And you're supposed to look away. Well, then the nurse would slap me in the butt and the doctor would jab me in the arm and never even felt the arm jab because of the slap in the butt. They were using the gait theory of pain. Well, phantom limb pain is I don't have an arm anymore, but I feel the pain because I still have the somatosensory cortex that is associated with the arm that no longer exists. But the somatosensory cortex still exists, And if I'm feeling, if that particular area of the somatosensory cortex is exposed to some kind of electrical signal that would have told me in the past that my arm is in pain, I think my arm is in pain because this is called phantom limb pain, because the brain is telling me so. And it turns out that the cheek is really close to the hand in the brain in that particular somatosensory cortex. And when you lose your hand, when it's no longer there, that area of the brain is not being used very much, and the cheek nerves sort of inundate that area, and when the cheek is exposed to an air blows by your cheek, it activates that area of the somatosensory cortex which was for your hand, and you don't have a hand anymore, but you feel like somebody just touched your hand. And you don't usually notice when the air blows by your cheek, so you don't notice that, but somebody touched my hand and you don't know why. That's why, because the cheek signals have been transferred to that particular area. It's all in your head, phantom limb pain. If you take a person that's lost their arm and put them in front of a mirror and they're having phantom limb pain and they're looking at themselves in the mirror and you've moved the mirror around so it looks like they're looking at the arm that doesn't exist anymore, and you stroke the arm that does exist, it looks to them like you just touched the arm that doesn't exist, the pain disappears. And this is a type of placebo effect, a substance that appears to be something that it's not, right? Your arm that isn't really there. The placebo effect says a response to a placebo, usually a sugar pill is what they talk about, which is caused by the subject's belief that they are taking a real drug. In this case, the belief that somebody just touched your arm because you're looking at your arm that isn't there anymore. And that's the end of this particular section. Are there any questions about this? If there are, you can stay and talk to me. If not, we're done, and I will see you next week on Tuesday. And otherwise, have a very good weekend. Stay healthy. Bye.